first of all, to welcome our speakers. Thank you to be here and to share your developments. So we will start with Riku Kopra. I hope that I'm not spelling your name correctly. And the title of this presentation is Experience and Results from TDS Measurements in Brown Stock Washing at Different Pulp Mills. So Riku is a senior researcher, scientist at Southeastern Finland University of Applied Science Fiber Laboratory in Savonlinna, Finland, and have been working during about 20 years in various research positions. He's also graduated from Tampere University of Applied Science and as engineering of paper technology, and also a master from Oulu University, and also from Aalto University as a doctor in science. So a lot of graduations, and also is published a lot of articles, namely or basically in brown stock washing, oxygen delignification, wastewater system, so a lot of work on research. So Rick, please, the floor is yours.
Okay, thank you. Please, Rick.
Thank you for introduction, Mr. Chairman, ladies and gentlemen. It's great pleasure to be here. And today I will present for you brown stock washing study, which consists of 10 different rough pulp mills. And I'm working in Oipo Laboratory, Savonlinna, Finland, and co-author Keijo Pyöräläis from Vaisala Corporation. And here is contents of my presentation. First I say a few words about backgrounds and the aim and target of optimizing and boosting pipeline processes and mainly brown stock wash. Then I show different wash loss measurement methods, mainly TDS, COT and conductivity, and benefits and challenges of these, and then measurement principle of process reproduction. Then result part, which it consists what kind of concentration levels goes from cooking to evaporation to brown stock washing line, and O2 delignification and bleaching. And finally, short conclusion. Thank you. So then little bit background. We have done pretty many brown stock washing studies where we have evaluated performance of single washers and also performance of full brown stock washing line. And we have mainly used total dissolved solids measurement by process refractometer as measurement unit, and also sometimes COD conductivity and lignin content measurements. So, little bit basic information. As you know, performance of washing has effect on many sub-processes like evaporation, O2 delignification, bleaching and wastewater treatment. And if we use a lot of wash water, evaporation, bleaching chemical cost and makeup chemical cost decreases, and pulp is cleaner to O2 delignification, but evaporation cost increases. So we try to find that optimal operating point where all these sub-processes are balanced. And we have to be close to it. So, why to boost or optimize brown stock washing in pipeline? Of course, the main purpose is obtain sufficiently clean pulp for developing sub-processes using minimal amount of water, so black liquor dry solid can be maximized to evaporation. And we also try to optimize the single washer's performance, dilution factor, wash water amounts, and one important is also consistencies. In the mills, we pretty often see that inlet consistencies are too low, so we can get not high good washing consistencies and outlet consistencies. And carryover also affects the performance of O2 delignification. It consumes oxygen from exothermic reactions, so we have to monitor also that. And also we try to optimize carryover to bleaching so we can save bleaching chemicals. And last but not least, we try to minimize also wastewater load to wastewater treatment plant, and if that limits production, then it's more important role. Okay, then few words about different measurements methods, and of course it's very important to understand what are you measuring and what are challenges and benefits of different measurement methods. And if we look at this figure, there is 1 to 10% dissolved material in the filters, and if we measure total dissolved solid, we are measuring all this dissolved material. COD measures only that organic part, mainly lignin and typhoid breaks, and conductivity that inorganic part. And that dissolved material is pretty easy to wash away, but we have to also remember that part of phosphorus is in the fibers, and that needs, for example, delays in the tanks. And there is listed some advantage and disadvantage of these measurements, and you can find more information about these publications. Then few words about process refractometer, what we used. It determines the concentration of solution by measuring optical refractive index using CCD cover. And it depends on the concentration of dissolved solids and temperature. And we are measuring refracted light between a test and protest old from that there is made at thicker angles, and we are measuring this optical image, dark sector and white sector, and then we know the concentration of solution. And because we are measuring refracted light, suspended solids, whitecaps, and bubbles do not affect the measurement results. And here you can see wiper lies under our investigations. There is listed washers which are in the lines and production levels during the test. Few mills are already closed, but most of is in the run. And then results. First, there is TDS and COD concentrations from cooking to evaporation. And left side, we can see that about half of the mill's dissolved solid concentration to evaporation was about 17.5 to 19 weight%, and dilution factor was about 2.3 to 2.8. 4 of the mills concentration level was 16 to 17%, and dilution factor were 3.0 to 3.5, and one of the mill I, there was little bit problem with washing, and dissolved solid to evaporation was only 13%, and dilution factor was about 5 cubic meter. And here you can see how that affects costing If we increase dilution factor by 1 unit from value 1 to value 2, evaporation cost increase on average 1.5 euros per pound dry ton in this experiment mill H. Then TDS COD concentration went from pulping to brownstock washing line, and here you can see that there is a lot of variation. And highest amount of dissolved solids from cooking to washing line comes with mill A and H, which both have batch cooking at maybe a little bit inefficient washing. And also recently there has been some trend in Scandinavian mills to extend the cooking zone at the expense of the washing zone, so we need now more efficiency for the individual wash. Then TDS COD carryover level to O2 delignification, and in the literature it has been said that 100 kilograms COD per ADT is good level, and if we look at this figure, most of the mills are working well, but in the mill D, H and I there is little bit problem with washing before O2 delignification, and 2 of these, D and H, are already closed, and this I mill has little bit problem, but they are solving this problem. Okay, what's that mean if you have too much carryover to O2 delignification? Of course, excess washing loss consumes oxygen for wrong reactions, and desired kappa reduction is not as steep. If we look at this figure, it's from mill H. When carryover was less than 250 kilograms, O2 delignification was working well, kappa reduction was over 30%, but when carryover was more than that, kappa reduction collapsed pretty fast. And from this figure, we can show how carryover increase temperature in the kappa reduction here. In this result, we measured that 10 kilograms COD means that temperature increase 0.11 Celsius degrees, and without this same result from it. Then COD dissolved ratio in the blow pulp and feed of O2 reactor, and this ratio is lower in the oxygen state feed than in the cooking area, because the organic matter in the wash water has already seen oxygen in the oxygen states. And this depends, of course, what alkali we are used, sodium hydroxide or oxidized white liquor, also what kind of performance we have cooking, and what is the chemical amounts in cooking. And when we know this ratio, we can use also process refractometer for measuring COD load to process. Then TDS COD carryover levels to bleaching, and in the literature it has been said that 5 to 10 kilograms COD is good level, and we can see that most of the mills are working very well. For example, this mill they can use little bit more water, but this mills there is problem with watering, but the these are what exposure. And this is the mill, which have also a little bit software reporting bacteria showing some impact. Okay, then conclusions. Brown stock washing affects the operation of several sub-processes and profitability of entire pulp mill. Therefore, it's important to monitor the success of washing with continuous measurements. And there is 3 different nations. What I today tell is the basics installation. We measure what is coming from pulping to transport line, which is going to auto purification, and what is going to bleaching, and this one what is going to evaporation. And next level, advanced level, we measure also filtrate concentrations from the washers, and at complete installation, and we measure also what is going to pulverization. Okay, thank you.
Thank you. Thank you. So we will proceed like this. So we are quite tight in time, and some of our colleagues in the audience, they probably have they are registered for Pavel. So we will rush now sequentially, and then in the end, please take your notes for the questions for each presentation, and then in the end we will make the questions. Okay? Thank you. So next presentation, that is entitled as Implementation of Online Ship Properties Analyzer and Digester Dry Ship Feed Rate Control. So by Thanh Trung, sorry if the spelling is not correct.
I'll get to.
So Thanh is the general manager for Fitner, a Voigt company, and holds a degree from the University of British Columbia, specializing in analytic chemistry and molecular spectroscopy, and joined some paper research institute in Canada, and have a long history. So I will not bother the audience with so long experience and your long research career. So please, the floor is yours. Please proceed.
Thank you very much. Thank you, Ricardo. Thank you for the committee selection for my paper as well. Take this opportunity to present some of our work. Actually, this is going to touch upon something that's actually very timely from what we just talked about, and that is looking at your fiber supply. We just talked about this in the last paper, or last plenary lecture. Fiber supply is one of the most expensive in terms of issue cost that goes into your digester, right? And this is going to be something that's going to be impacting a lot of our production. And often, in terms of chip and chip properties, we don't actually do very much with it. We have a measurement on the moisture that might take several hours to do, or if at best, maybe overnight drying and give you some information. So what I'm going to do is just describe to you a little bit about what we have done in terms of providing an online measurement capability to actually provide you with information that's necessary to do digester feed rate control, production rate control. So let me get into it a bit. First, I'd like to thank my authors and co-authors for the paper. So a bit of introduction in terms of the importance associated with the chips and why it's actually important for us. Current methodology associated with the system that's for measurement, and then we'll go a little bit more details with regards to how this is being used, how are we doing this analysis, what type of technology we're using, the principle of it, a little bit of a setup, look at the installations, the results, and then we're going to actually have some applications in how this is done for feed rate control. So, some of the biggest factors that actually influence digester operations. Obviously, your white liquor, your residual effective alkali down the digester. But what's actually feeding into your digester? Two things. Obviously, your white liquor, so your EA is very important, and of course your chips. right? But we break down to chips, you have species, anatomy that has an impact, size distribution also has a huge impact associated with this. So if you're not screening, that's what you should be really doing also. Quality-wise, chip moisture, obviously, buffering capacity, density, all of those components, not very often measure, if at best, some lab testing and so forth. But of course, all other things such as time, temperature are very critical. All of these affect your kappa, and all of these affect your yield. Okay, that's very important to understand. So in terms of characterization-wise, it is, in terms of the most expensive part of your mill, often 30, 40, in some areas 50% of the cost of producing that ton of pulp. And as we just talked about previously, reducing that cost is going to be one of the most important aspects associated with this in terms of maintaining operations for the mill, maintaining the viability of the mill. Okay. The size, the impact, obviously, chip density and extractives have huge impact, and the better knowledge associated with the feedstock provides us with the opportunities to actually optimize the process. And of course, ultimately, to reduce costs, but also to increase production rates, reduce downtime and gain efficiencies associated with this. But what are some of the extra systems available right now? Often you'll see manual grab samples we talked about. These are typically oven-dried techniques. You go out there, you take your samples, or you either measure it from the chip pile or on the belt itself, or maybe even applications associated with this, grabbing samples at the trucks. All of these are very slow and onerous testing and takes quite a bit of time. Gamma radiations, nuclear sources radiations, you've seen those in the past. They are being phased out actually because of the fact that you have a lot of aspects associated with tough regulations and hazardous means of actually working with these sources. Microwaves show some promise. There's quite a bit of drawbacks associated with these in some of the trials that we have done and others have done, particularly the area in terms of how do we actually compact the sample enough to give us the information for the measurement of the moisture properly. If we're talking about areas that have snow, such as Finland and Canada and so on, where we're minus 40 degrees in the winter, how do we deal with those scenarios associated with frozen chips? That's another aspect associated with this. There's quite a bit of talk and trials about the use of what we call as filtometers. Filtometers are also NIR based, but they're single wavelength systems. So these essentially you have a filter that has windows on these, and as it rotates, it filters out certain wavelengths. And the idea is that you would select the wavelengths that's most sensitive to water. But the problem is that these things are very, very low in energy. You filter out most of the energy already. These are suitable for maybe more homogeneous sample, maybe in foods application. Very difficult to maintain calibrations, but the benefit is that it's low cost. The problem is that as our materials, the chips itself, are very natural products. It changes all the time. Where do we come from? Where are the chips coming from? These things change all the time. Whether you harvest on one side of the hill to the other side of the hill, sun, water differences change a lot of the properties associated with these. So they don't actually work very well. So our challenge that we put ourselves was, how do we do this to allow us the measurements that can actually happen in all different scenarios? We decided to go to a full spectrum system. Our range is typically from about 1,000 nanometers to about 23, typically 2,500 nanometers. We wanted to be able to do this on the conveyor itself, non-contacting. So a lot of times you see applications out there where you have things that are sticking into the actual chips on the conveyor. But the problem is anything that's breaking and falling into that's going straight into the digester, that's a major problem associated with that. Transfer models has to be robust enough, has to be fast enough measurements, and of course it has to be able to span large ranges, both frozen and unfrozen material. So that was our challenge. We chose to go with what we refer to as a full spectrum NIR system to provide this type of measure capabilities and so on. So we talked a bit about light already in terms of how it interacts, and in this case here, in particular in this case here, our aspect is we're looking at what we refer to as diffuse reflected light. Okay, so we have reflection. Reflection is what you see yourself in the mirror in the morning, whether it's good or bad, so that's your judgment. But obviously diffused light is a little bit different. The diffused light itself interacts with the sample, and when that light interacts with the sample, it actually absorbs the molecules and it absorbs some of that energy, and that induces what we call as molecular vibration. So that's exactly what we're using in terms of our techniques here. And in this case here, if you actually now are into spectroscopy, near-infrared spectroscopy is used right now in the James Webb Telescope, allowing us to actually see much better information in space, but also more importantly, to provide us with the actual chemical compositions of the actual gaseous planets out there, stars and so forth. So our spectrum comes back to us. It interacts with a sample. A depth of penetration into the pile or on the belt is typically about 4 to 5 inches. That diffuse reflected light comes back to us. We collect this, and it produces the spectrum. And this spectrum contains the unique information that we're trying to actually do to actually calibrate this. So here's an example of the actual spectrum from about 1100 to about 2100 nanometer right here. And what you see here is differences associated with this in terms of moisture content. And here, 2 major peaks shows up around 1410 to 1920 or so are the wavelengths that has the most abundant information. But reality is there's actually quite a bit of other information that shows up. And you actually apply this to pulp sheets. You can pick up cellulose, hemicellulose, crystalline cellulose, a lot of other information. But in order for us to actually calibrate these things, we actually have to go back to our challenge. How do we do this in various conditions? And what we did was, in this case here, is that we actually changed the temperature. So the diagram for the experimental plan in this case here is that you see temperature variations about minus 25 to about 38 degrees or so at the various levels of moisture content. Okay, so that's, you train the system to recognize the actual water absorption features that allows you to actually quantify the concentrations of water in the chips. And what you see are these. So you see that the changes now, in this case here, is the temperature related to the temperature. So the color itself is related to temperature. And as you change the temperature, the peaks associated with the water actually shifts. And that makes completely sense because of the fact that we're looking at the absorptions of the water. Free water absorbs differently than frozen water, meaning that it actually requires different energy, different frequency to actually vibrate these molecules. So you actually can tell whether it's frozen or unfrozen, and you can actually use this to quantify the actual water content in the chips. So calibrations are done with these large range scenarios where we have essentially from very large low to very high concentration ranges in moisture content, and the color differences associated with the fact that these are both in terms of unfrozen and frozen materials. We implement these things all into the process, we measure these things, and we validate these results associated with this. And again, the color indicates whether it's frozen or unfrozen materials. So the concept here is that we have to be able to actually measure it in both environment to be able to see both free and frozen water. The system integration looks something like this. We have an online system. We have a sensing head that's mounted over the conveyor system. It shines light onto the actual belt itself. The diameter of that illumination spot is approximately 6 inches in diameter. The light that comes back to us is our diffuse reflected light, and we actually collect this through our fiber optic cable and register into our spectrometer. We've improved on this further. We started with this fixed scenario associated with the actual arm itself. Our latest system now actually has a distance sensor in this as well, so that it will actually float and actually keep that optimal level whether you have low or high production. So the initial system was at a fixed height. Now we actually have a system that actually move up and down and actually optimize the actual distance to maintain that optimal illumination spot for the light interaction to occur. So what we saw there was that when we go really low production, that distance becomes too low, and that's why we actually optimize that using the sensing scenario. Light comes back to us at the cooler, the cabinet itself that houses the actual spectrometer. We have heater and cooler system, as I mentioned, mainly because we have frozen conditions. Interacts with our computer system. Our computer system quantifies and analyzes the data, quantifies the spectra, and basically gives us the information associated with the concentration. How it integrates is this. As I shown, the ProPED system, fiber optic connected to the spectrometer, which is then connected through a PLC Modbus scenario, fiber optic connected to the MOXA connection here, back to the DCS itself. So all operations, all data gets integrated back directly to the DCS. One of the big concerns associated with this is that if you were to have a scenario where the belt stops, what would happen? In this case here, it has a specific trigger. That belt stops, the actual light source itself will turn off to ensure that it don't continue to heat the actual chips itself. For example, possibility of fires and so forth. It's not that hot, but it's well integrated to ensure that you have a safety perspective associated with it as well. So these systems have been implemented for quite some time already. Our first installation in Canada at the Alpac mill, Alberta Pacific mill, has been about 8.5 years into the operations of the system already. We have systems all over the world. Here is just an example of the online analyzer system working on chips. Initial early phases, we had to finish the model, and once you actually complete the model algorithm associated with this, you can see that over the data set here is this 2023 from 2019 trend associated with the actual validation results from the instrument and the laboratory results associated with this. So measurement's fine and dandy. It's just a measure. What do you do with it? That's the real question. And the idea, what we talked about earlier, is to actually provide means of reducing costs. In order to do that, we have to implement some sort of actual control algorithm, okay, for allow you to actually make changes to your operation to save money. So the application associated with this is that now you have the moisture content. What are we going to do? We're going to provide means to actually do what we call as production rate control. Conventional control basically takes the moisture content, but as I said earlier, maybe done once a day at best, maybe once a week, that information, but along with other things such as chip meter speeds. This is known. What do we do with the actual density associated with this, the bulk density or the basic density? How do we deal with those kind of things in terms of the actual chip in here, in the chip bin, chip meter silo? The fill factors, the wet density, the moisture content, obviously assumed but measured on a laboratory basis. So that's conventional control. The problem associated with this is we can't control the chip meter speed well enough with this information to provide accurate information to the digester loading of the chips. So what we've done with this is that we've taken the analyzer results from that moisture content along with the weight on the belt that allows you to calculate the dry mass. And that dry mass allows you to now calculate from the perspective of the control, back to a controller here, to maintain and operate that chip meter speed so that you actually get to your target point associated with your production target. Okay? So that's the trick associated with this. We talked about the density and so forth later on. That's still needed, but in the case here, we can actually, I'll talk about the measurement associated with this next. So what happens in the case here in conventional control is that if you have a production rate, I'll explain this line here, there's your target in yellow. Okay? That's your target part in yellow. This is on manual control in terms of the actual chip meter speed. Often what happens is that if you have an assumed value, what you see is that the actual calculated feed rate to the digester is actually under the actual target itself. Okay? In other words, your assumption associated with this is not correct. Therefore, the loading into the digester is incorrect. Now, this scenario is actually quite bad because what happens here is that you're undercharging. You have extra amount of white liquor because you guys have an assumed EH wood liquor ratio. Therefore, you're actually consuming and dissolving more of the actual cellulose associated with this, the carbohydrates and so forth. Okay. The other side of this is actually also very bad when you actually go above that production rate. Now you're basically charging too much chips into it, not enough white liquor. Therefore, you have a hard cook scenario. So as I mentioned, controlling that portion has a huge impact on your overall yield and kappa. So what happens is in this case is we implement this control strategy. The idea is that you would manipulate that chip meter speed so that you maintain that target production on control. That's how you would actually use something like this. You can actually implement this obviously without the analyzer, but you have to have sufficient amount of speed to actually provide the moisture content necessary along with some of the other assumptions associated with the density and so forth. This resulted, and is actually reported by the mill. I can share the report with you, and result in significant amount of saving for the mill in terms of production rate for the mill. So the case study here is that what we saw was about, boil the story down, reduction of variability in kappa, but more importantly, a 4% increase in production for the mill. And that was actually very, very significant for the production of the mill. But as we talked about earlier, there are some other properties that are needed. That bulk density, that basic density, all the extractives and stuff like that, that's still needed. And there was an assumption. So the mill came back to us and said, okay, let's develop this further. I wanted to actually see some other properties associated with this. So we worked with them to develop further in terms of the actual measurement. And what we came up with is actually using spectroscopy to actually allow us to actually come up with other properties, such as the bulk density, such as the basic density. That's obviously going to be another input into that control strategy. Okay. What's also important is lignin content. So we were able to actually develop the measurements for total lignin, soluble lignin itself in terms of the density associated with this, and of course the extractives content with the measurement. So these assumptions that we had earlier in the control strategy now has the input associated necessary to actually run that on a continuous basis. So summary-wise, the online chip analyzer over the years, it's been running, as I mentioned, at Alpac for over 8 years. Very, very good results. We did have to add that one capability to the actual sensing head, as I mentioned earlier, to allow us to actually float with the various production rate. It was most of a problem when it's actually going very low production, when the distance was too high. But other than that, it was an improvement to the overall system to give us the illumination spot that's always optimal. The data validate very well in the case that I provided to you over 3-4 years in terms of data validate very well for the chip moisture. The output help with the control and applying it to production rate control, and that saw a tremendous impact for the mill. And so we've further expanded this system over the measurement for chips to provide things like bulk density, basic density, as well as lignin and extractives content. And that's it. My contacts here. If you have any further questions or anything like that, feel free to reach out to me. And then we can have a little discussion afterwards. Thank you.
Thank you. Great. Please take notes for the questions. Very interesting presentation. Thank you. So next presentation will be done by Kiran Baddigam. And is entitled CO2-assisted chemical pulp, a pioneer approach for high-yield lignin-rich pulps. Please.
Yeah, thank you for
yours.
Kind introduction.
Yeah. Sorry, I didn't present, but so Kiran has a PhD in chemistry and currently researching as a scientist at VTT in Expo, Finland, and I have several works on the work centers on the research and the development, mainly in the sustainable biomass processing and bio-based materials, and so on and so on. Please go ahead.
Thank you for your kind introduction. I'm happy to see a big number here. Thank you for your interest in our pulping concept. Today I'm going to talk about CO2 assisted chemical pulping, a pioneering approach for lignin-rich high yield pulps. So I work in a biomass processing team in VTT, and VTT coordinating a big emission free pulping program. It's launched in 2024, where the main idea is to improve the value creation from wood feedstocks, because we have a limited biomass source and we have to utilize in a much efficient way towards high product yield. With that challenge, the emission free pulping program come up with 30 researchers and 15 million euros fund. In that, 1/3 comes from the private organizations, and what they deliver at the end as an impact on this, in this pulping field, they are planning to create a new knowledge and generate a next generation pulping concepts. That is one thing. And of course, the CO2 emissions are the key thing to minimize and keep the present chemical pulping yields where we have 50%, and this emission free pulping program to upgrade that chemical yields to even further higher, that is 70%. That's the main goal. And who all are involved in this consortium? There are 7 industrial partners and 10 research organizations. They joined together to tackle these challenges, and in that, our role as a VTT, we run a parallel projects, and today the high yield chemical pulping that I am presenting, it is one of the parallel project, and our colleague tomorrow, she will present on mechanochemical pulping. The Angeliki is here and she will present tomorrow. And now I would like to jump into the main part. The main goal of this project is CO2 chemical pulping, where the aim is to improve the high yield chemical pulps. Currently they are somewhere around 50%, and we would like to keep this even further higher, which aligns with the emission free pulping goal. And the sulfur based emissions, that is another challenge to address, and with our new pulping concept, we make sure in the feed chemicals we avoid the sulfur based cooking chemicals, so that we aim to make a zero sulfur based emissions at the end. And the another point here is the chemicals that we introduce to achieve this high yield chemical pulps, that should be easily recyclable, not to react with other components, and further we can use it for next batch cooking. That is also one of the challenge we consider. And the process, once we develop the process at the end, that should be easily adaptable from the industries. So we focus also on feasibility, how this can be runnable in a mill scale. That is one thing. And the another challenge, that is CO2 emissions, water, less water consumption and less energy. That also I will touch one point of time in my presentation. And now our approach, how to achieve these high pulp yields. If you look at this picture, the wood chips are quite hard. We need to soften enough to liberate the pulp from the wood chips. That is the important thing. To do that, we need to break the outer layer, that is the lignin. How we can do this? These are the 3 molecules I bring here. CO2, it's a gas phase, and the water, ethylene glycol as a organic solvent. So with these 3 components, how we do the pulping, what are the each component role here? The CO2 here, it can act as a gas catalyst, and ethylene glycol here, it compensate as a co-solvent, and the major solvent here in this pulping process is the water. And this process is completely metal free. You do not see any kind of metal based inorganic chemicals to cook the pulp. And one more point here, since we do not use any sulfur based chemicals in this, so we aim to get a zero sulfur based emissions at the end. And the water consumption, when we do not use these metal based salts, then we are expecting that this process consumes a less water. That is one interesting point when compared to the craft. And now you can see how this recipe is going to work. This is the background chemistry. The CO2 at high pressure levels that dissolves in water and generates the carbonic acid, and that carbonic acid initiate the reaction, and it influence on the aryl ether bonds in lignin, and it partially depolymerize. That is the thing. And where I have taken a lead on green chemistry, where we showed how this CO2 chemistry work and depolymerize the lignin. You can go through this reference article. And another point here, I would like to bring the ethylene glycol. What is the role of ethylene glycol? The ethylene glycol having a effective impregnation into the wood chips. When the depolymerization starts, the ethylene glycol try to dissolve this liberated lignin and soften the wood chip and keep the rigid wood into the fiber liberation point. That is the thing. And why we have chosen the ethylene glycol selectively? What are the key benefits of using this ethylene glycol? So this is not new to chemical industry, the bringing ethylene glycol into the bulk scale. Even pharma and other different sectors, they are already using ethylene glycol and getting the benefits of those. Why don't we introduce this ethylene glycol into the pulping sector? That's the idea. And another important thing here, the solvent based approach, we go with this ethylene glycol. And when we compare the solvent based approach with chemical based pulping, mainly the solvent here, it shows a dissolution based mechanism and it's a mild reaction. When we see the inorganic based chemicals for pulp cooking, the reactions are much vigorous towards the lignin, and once we produce the pulp, the used chemicals, whatever these salts, that is dissociate into corresponding ionic forms or some other chemical forms. We need an additional steps to regenerate the chemicals. But in case of ethylene glycol, in our approach, the ethylene glycol is quite stable, and once it does the job, again we can reuse and recirculate into the next batch of cooking. That you can see here clearly. So we simplify the pulping process using our CO2 glycol pulping approach, where with simple vacuum distillation and evaporation processes, we can reuse the used solvent and used chemicals into the pulping. And where in the craft process, you need the causticization, lime killing, and these additional steps are required to regenerate the chemicals and use it for further. That is the main difference between these two. And this is our early idea of fiber line flow chart, where we feed the hardwood, that is eucalyptus and the birch wood, and we get output as a brown pulp, that is called high yield pulp. And the cooking conditions, you can see here, the 170 degrees centigrade, 2.5 hours, and it's a quite acidic pH 3 to 4. How we do this? We use the industrial size wood chips. We have a standard operating procedures at VTT Pilot Center in Finland, and the oversized and the fines we remove, and rest of the chips we mix it and use it for the pulping, the way how industries they use in the mill. Here you can see the hard wood chips, the screened wood chips, birch and yucca. We cook under the high temperatures, 2.5 hours, and wood to liquid ratio you can see here 8:1, and the CO2 glycol in presence of water, these wood chips are well soaked and the chemicals are well impregnate into the wood structure and helps to liberate the fibers and generate the pulp. That is the main idea, and this is how the ethylene glycol significantly influence on softening the lignin and liberate the fibers. What will happen if we don't use at all the ethylene glycol under similar conditions? To understand this, we run two separate trials. One, we cooked only in water without in the presence of ethylene glycol, and another trial, water and the CO2, carbon dioxide gas, we cooked under same conditions, and where we end up with the rigid wood chips. These are quite strong and it's not enough to liberate the fibers. It's like still in a wet form. So this is very difficult to liberate the fibers, and the ethylene glycol is mandatory to soften the chips and liberate the fibers. That is the idea. So without ethylene glycol, this pulping is not possible. And now the next step, what we did, we sequentially reduced the concentration of the ethylene glycol and we increased the water concentration, and that is how we gradually reduced the ethylene glycol chemical from 50% to 10%, and we generate different pulps, ethylene glycol cooked, 50% ethylene glycol cooked pulps, and the 30%, 20% and 10% ethylene glycol cooking pulps. So by this way, we benefit the techno-economically feasible and economically viable process we aim to generate using this approach. And here are the results. The pulp yields, in case of birch, you can see here birch 50, EG50, indicating 50% ethylene glycol based cooking, and followed by 30, 20 and 10, and the yields are varying in case of birch, but still it's maintaining somewhere between 60 to 65% yields. But in case of eucalyptus, we completely lift it up, the yields somewhere 81 to 86%, where we use ethylene glycol 30% and ethylene glycol 20%, because these are really a very good results compared to traditional pulps where they have the yields 50. We almost put a yields 25% higher than what we have at the current processes. So this ethylene glycol is really influencing on this. And the next point is the viscosity. So where the viscosity stands when we cook in presence of acidic pHs using ethylene glycol in presence of water, still the intrinsic viscosities are alive. So it's not like there is a huge window to further develop these pulps the way whatever the end applications the industry is looking for. So that's why these intrinsic viscosities plays a key role to address whether this can be useful for high value applications or where we can put these kind of pulps. And the kappa numbers you can see here, the kappa numbers are varying 92 to 166. That is one thing, and overall the results are interesting, particularly the yields, since we are focusing on yields, and the ethylene glycol approach plays a key role in preserving the carbohydrates. And what we did, all these laboratory scales, we scale up to the mini pilot scale and then produce the pulps, and these pulp, in case of birch, the yields are consistent with the pilot scale results. And to switch these processes to the further industrial scale, the techno-economics plays a key role to see where how much ethylene glycol we can recover, and in that way we can estimate how much cost estimation on producing these pulps at the mill scale. So currently we are studying the techno-economics, so that is what I would like to mention here. And in conclusion, so far we used hardwood chips that we received from the industries, and the yields are 64 in case of birch pulps, and eucalyptus giving a very high yields 86%, which is really excellent and almost a 25% higher than the present market pulps. That is one positive thing. And the ethylene glycol is really a key role in preserving the carbohydrates in this process. And initially we worried about the pH. This quite acidic pH can have a possibility to cut down the cellulose, and that would affect on intrinsic viscosities, but that is not the case here, and viscosity is still it's maintained, and the pulps, the conditions that we employed here, the cellulose chains are surviving. And now we are doing the refining treatments to understand the pulp behavior and the strength properties, so that where we can switch these pulps and what kind of applications we can look for. That is what we are looking at the moment, and the techno-economics and LCA results are on the way. And I greatly acknowledge the technicians team and also the Repower the funding comes from the Repower EU project and the emission-free pulping program. And I highly acknowledge the VTT's tremendous support in this entire journey. And this is our team. Please feel free to reach us for further collaborations. And our team manager is here, Liji. So thank you very much for your attention.
Thank you. Thank you. Very, very promising process. So before we start the questions and answers, of course, I have an important announcement here for the ones that are registered for paddle. I hear that you should go to the bus in front of the hotel, and with your personal equipment and the change, it will be on paddle facilities. Here, that bus leaves at 18:15, but since that we were a little bit delayed, I hope that they have a certain tolerance. But for the ones that have this paddle activity, please be aware of that. And of course, for today and for the other events, that take a look on the cell phone for the app, because the app, it will send some message for other proposals. So about questions, please feel free, and we need a microphone, please. Okay, it's already with you. And for the audience, there are another one. Please.
Yes.
Okay, we can sit, please. For the audience, I think there's someone that can help. Okay. It's working, that one? Other one, okay. Yes, I can. Okay, thank you.
Okay. First of all, nice presentations, very interesting. I'm a pulp guy on the ground of the mill, so quite nice presentations. Congratulations all of you. Okay. My first question is for, sorry, I cannot say the implementation of line sheet properties. I'm a digester guy. Well,
Yes.
24 hour almost sometimes. And it's quite impressive that you've shown. First of all, the feasibility of the equipment is very resistant, because we know there are always a lot of dust, stones, and something that sometimes is not going to there. So it is very feasible, very, how do we say, resistance to this kind of environmental issues.
Good question. Let me,
Yes.
so I'll pass it back to you. Thank you very much for the question. Appreciate that. Yes. So with regards to the actual uptime associated with the analyzer, that's actually quite critical. And typically we work with above 98% uptime associated with these systems. Now, specific to your question, it's actually very legitimate, and that is on the dust and this so forth that actually would potentially affect the windows and the lens. So we found that early on that you have to keep the dust off that system, but it actually works really well in a sense. Two things. First, near-infrared regions that we're looking at is what we refer to as long wavelengths. And the reason why the long wavelength works better in dusty areas is exactly that. You can actually see through the particulates in the air. And that's actually very important. So if you go back to applications, military applications, I was involved in the military applications, you have to see through sandstorms. Our near-infrared cameras can actually see through sandstorms because of longer wavelengths. Very similar to radio waves. The reason why you can listen to radio frequency inside the room is because it's longer enough wavelengths. You can penetrate through walls. And why you can hear AM instead of FM in mountainous areas, because you have longer wavelengths. So that's the first thing. Second, we designed the window in an angle format. So if the chips are flowing in this direction, the wind is coming up in this direction, we design it so that we have a bar in the front and an angle. So what happens that the wind actually hits the angle, the vertical section, and as it drops away, it creates a vortex. so it actually doesn't impinge the material onto the windows. So that's the second thing that works really well and actually keeps the dust off. One more recommendation, do not use air knife. The issue with the air knife is that when you actually, do you know what an air knife is, right? That's it puts air into it. The problem is that it actually causes and accelerates the particles to impinge onto your windows. And it also causes a change in the temperature of the window, and that further exacerbates the problem. So we engineered very much like a airplane a wing, where you actually cause a vortex, or at least a low pressure in the back that actually doesn't impinge on that, and it works very well. So typically we say every 6 months come out and check on it, and then we change out the light source every year. Good question.
Okay.
Do you have another micro or no? Not really. Okay.
Another thing that, in my particular case, my mill, we use hardwoods and softwoods in percentages, and that's due to some problems in the supply. So that means if we have more or less 30% hardwood and 70% softwood, could this equipment also take the densities? Maybe the variation densities, because our problem, in addition of this, of the pressure of humidity and so on, is also is ratio between the fibers, because we use more or less 30% soft hardwood and the 70% softwood. So in addition to all of this, even these variables are big.
Just to do something. And the keep says that we are answering. Yes.
Well, that's another excellent question. So first and foremost, in terms of the humidity, the moisture content is not affected. And the reason for that is because we are looking specifically at those peaks that I mentioned, and that peak for water, whether it be at 1410 and 1920 wave numbers or nanometers, is the same whether it's hardwood, softwood, because we're looking at specifically at the molecular vibrations associated with that. So moisture content is not affected. Yes, the actual density will change, okay, because you have mixtures of those, but you could actually generate, and we have done this, and that exact Alpac mill is actually a hardwood, softwood mill. It swings back and forth. So what we've done for them is we actually calibrated the system to actually give you a pseudo number of distribution of whether it's 30, 40, or 50% hardwood or softwood. And I say that it's because when you do manual scrap samples, you actually determine whether it's 40, 30, 50. You have to be very careful where you collect, because size distribution might be different, even though it's softwood, hardwood. You have segregations as you lay them on, so you got to be really careful about that. So yeah, we've done that where we actually also provide a distribution of the actual hardwood, softwood components.
But do you have to reach percentage to have a third?
No, it's universal calibration, especially for the moisture content. It's all the same. Yeah, that doesn't change. That was a big challenge for us too, to be ensure that we can act, because in Canada we use a lot of hardwood, softwood. The hardwood size is aspen and poplar, as well as maple as well. So maple was the bigger challenge, but it turned out actually very good, because the maple itself has a lot of extractives, and that actually we were able to actually pick up the extractives on those very, very well.
Okay. Any further question? Please don't be shy. So very interesting presentations.
Yes.
Okay. Sorry. Yes. I'm seated too long time. What is wrong?
The presentation from the CO2 cooking is very, very interesting. Quite following your work, how do you recover the ethylene glycol in the recovery boiler? Sorry, maybe it's not the recovery boiler, but as another kind of recovery boiler. How do you, because our current craft pulp is sustainable because we recover chemicals. That's the basis of all these chemicals, okay? So the recovery of the ethylene glycol has to be very, very good to maintain this economically feasible. Or so that's the first step is made. You can cook it, but now the second stage, I think, my point of view, is how we recover so that this can be feasible and economical, interesting. Do you think of what is? But because the first step is the hardest to cook, and it's quite promising, the high yield and so on. But the next step also is, in my point of view, quite.
This is a really very interesting question. Yes, that is true. The ethylene glycol recovery is the main key thing to see the success of this pulping. We are working on two ways. One is the techno-economics, by looking at in literature how much knowledge we have on ethylene glycol recovery, not only in the pulping, in some other sectors where they use water and ethylene glycol mixtures. And experimental values obviously will tell you the real numbers compared to modeling. And we are looking at the distillations where it can support, and all the liquors that we generate from our pilot trials, that we are planning to switch to the distillations, because in VTT we have a state-of-the-art distillation setups. So we are in the process to do.
It's not like burning the.
No, yes, distillation, because these solvents, the boiling point of this ethylene glycol is quite high, even 3 times higher than all the organosol based pulpings that they do in the present academia or many industries. So they use ethanol or acetone, this kind of acetic acid cooking, these things they do. The boiling points are quite low, but ethylene glycol boiling point is very high, 197 degrees. That helps not to lose the solvent losses at the operating in the mill scale. So that would benefit the solvent losses, one thing. And second thing, the simple distillation process, that simple, it will recover from the water and reuse for that. But there will be some kind of makeup needed. How much makeup is needed to compensate, that will be the game changer here. So it's a bit early to comment, but it's a very good question.
Yeah. We have the question of the actual politics does. Other thing that technology is the actual energy. So technically also is this key best lightning with energy for. And thus in installation has the key separate.
Yes. The lignin is a solid component, and this lignin having a good solubility in ethylene glycol. So when we distilled out the ethylene glycol, it will evaporate and condense and collect it into the another chamber, and then here the lignin and other chemical related stuff, it will stay there. But here the most commercial part is the value of the lignin. The craft generates the modified lignin, but this organosol based one produce the high value lignin that can be switchable to cosmetics and high value applications. That will compensate. Yeah.
And that basically is the last question. That is the to deal with the alcohol. We don't know that alcohol has like very well point, so was addition decrease. So I think this operation you are studying from the concept. That's good. Now that we should be revised. How do we maintain separations in this can?
Well, yeah. May I know what do you mean the concentration?
We put the words that need concentration. And then you set it all, but you can get the storage, the subject
Yes,
storage, you build it, all
exactly. Yes.
concentration, then
Yeah. So this all the solvents that I mentioned, acetone, alcohol, other than this glycol, they are flammable, highly flammable. But this ethylene glycol, that's why this is not highly flammable compared to those solvents. This is not that much flammable. It is completely safe to cook the pulp in the current pulp mills. That is what we are expecting. And this ethylene glycol, that's why we screened not to produce the pulps with 50-50, 1-to-1 ratio of water and ethylene glycol. Even we lowered up to 10% ethylene glycol and rest of the 90% water, which makes completely safe cooking. Yeah.
take Joel.
Yes. Thank you. Any further question? For Riku, that is also these measurements in brown stock washing is also promising to decrease a lot of chemicals in bleaching. Any question? So I think it's quite a long day. Everybody travel. Thank you for your presentations.